Hi students. Now our topic is here Anderson bridge. Here this Anderson bridge is used to measure unknown value of inductance. To measure the unknown value of inductance, this Anderson bridge is used. So this is the existence of Anderson bridge. Now I will represent it names, arm names. Here inductor. So I'm representing this as Alex, unknown value. So Alex, it is resistor Rx. Rx is the resistor, and here it is a. I'm assuming here it is a second arm, so it is R2 resistor in second arm. It is third arm R3 resistor in third arm. It is fourth arm R4. It is fifth arm R5, and it is a capacitor C. And the terminals are here. Here it is A, it is B, it is C, it is D, and it is E. These are the terminals A, B, C, D, E. Here, to analyze this Anderson bridge, we had to make simple modification in the circuit. That is, look at here, it is in the form of delta, that is between the terminals E, C, D, in the form of delta. Now we have to convert this delta network into star network. Then we can easily simplify Anderson bridge. So first I will convert this part into star conversion. So I'm writing this portion only, that is between the terminals E, C, and D only I'm letting. So I'm drawing here separately E, C, D. So between the terminals E and C you are having capacitor. Here is the capacitor. Next here is the resistor. Resistor, and here one more is resistor R3. So here the terminal names are, here it is E, so E, here it is C, so C, here it is D, and its name between the terminals C and C is capacitor C, between the terminals E and D is R5, between the terminals here R3. So now I'm converting this delta network into star. So I am assuming here origin O. O is the origin. Now the impedance between these 2 points, that means this point and this point, between these 2 points I'm representing as Z impedance between the points O and E. So it is ZOE is the impedance between O and E, ZOE. Now, the impedance between these 2 points I'm representing as Z between the terminals O and C, ZOC. Now, the impedance between the terminals these 2 points, here it is Z between the points O and D, ZOD is the impedance. This is the impedance. So when we see this, it is delta, it is star, delta, and it is star. Now I'm converting delta to star conversion. So simply I'm writing the formulas for each and everything here. When we seen here, just simply you have to write formulas for each impedances. First, Z O E equal to, from this one, ZOE equal to this one into this one. That means ZOE is existed in between R5 and C. R5 and C. ZOE is existed between R5 and C. So this one into this one by total components, this one plus this one plus this one. That is the existence. So ZOE equal to this one R5 into this capacitor. Its equivalent value is 1 by j omega c in terms of AC point of view. Capacitance equivalent value is 1 by j omega c in AC analysis. Just remember that. ZO capacitor equivalent value is 1 by j omega c. So R5 into 1 by j omega c. Just if you want to write it here, then you can write 1 by j omega c for the capacitor. Now this one into this one by total resistance here R3 plus R5 plus one more component 1 by j omega c. It is ZOC. Now ZOC, I will write here conversion formula for ZOC equal to, look at here, this ZOC is existed between this C and R3. In between, look at here, in between these two are having this one. So ZOC equal to R3 into 1 by j omega c by total. R3 plus R5 plus 1 by j omega c. And now ZOD equal to, now look at here, this ZOD is existed, look at here, in between R3 and R5. ZOD is existed between R3 and R5. So ZOD is equal to R3 into R5 by total value again. R3 plus R5 plus 1 by j omega c. Like this, we can convert this star connection in from delta to star. Now I'm modifying my Anderson bridge with this. That means I have chosen this part. This part I have chosen. So now I am replacing this part with my equivalent values. Now look at here, between C and D. Between C and D, that means this one and this one, we're having ZOC, ZOD. Just I'm adding. Just I'm adding here. Look at here carefully. Between C and D, I'm having, look at here the path. This is the path. It is started C from this point, C and D. You are having ZOC and ZOD, C and D. So now I am replacing this circuit with its equivalents. Now look at here, simply four terminals are there. Look at here, A, B and B. Between A and B, here the terminal names here, it is A, B, C, D and E. These are the terminals, A, B, C and D. These are the terminals. Between A and B, there is no modification, so I'm writing as usual. Between A and B, same components L and R in series, so I'm giving here L and R. No modification between A and B. And between B and C, R2, no modification is also there. So between B and C are 2, no modification. Here it is A and B, Alex, and it is Rx. B and C is R2. Now, at the same time, between A and D, A and D, no modification. So keep it as usual. A and D, no modification. So keep the component as usual, and its name is R4. R4. Now, this network, this network is changed right now. That means between these 3 points, the network is changed. So I have already discussed here between C and D, we're having ZOC and ZOD. So just carefully look at here carefully. I'm writing here. Here it is. Between C and D, ZOD, ZOC. Just from this I have written here between C and D. Look at here. This is ZOC, ZOD. In between these two are having O. In between these two are having O. O. And one more point, between O and E we're having ZOE. So it is O, it is E. In between we're having ZOE, ZOE. And as it is here, B and D you are having detector. So B and E you are having one detector. And between A and C, source. Between A and C, source. So it is the modified circuit of the Anderson bridge. Modified circuit. Now when we seen this, let us assume it is the first arm, second arm, third arm. Third arm is from this point to this point only, and it is the fourth arm. From these four arms, I am writing here the first arm Zx equal to, from this one, from this arm Zx equal to Rx plus j omega Lx, because these two are in series, and Z2 equal to R2. And third arm Z3 equal to ZOC. Here we have chosen the third arm as ZOC only because the detector is connected at this point. That means it is the potential, that means it is the parallel existence. So we have chosen only this one. And Z4 equal to, fourth term equal to R4 plus ZOD. These are the four impedances from our bridge circuit. Now these four impedances has to be submitted in balancing condition. Balancing condition. Here the balancing condition is the product of opposite. These two are opposite, these two are opposite. Here it is the first, that means Zx, Z3, Zx, Z3. Balancing condition Zx, Z3 equal to, these two are in opposite. Here it is second, Z2, it is fourth, Z4. It is the balancing condition here. So now I am substituting those values in this and I am simplifying. So by substituting here, Zx means this one, that is Rx plus j omega Lx, into Z3 means ZOC equal to, Z2 means R2, Z4 means R4 plus ZOD. Now I am substituting ZOC value and ZOD value here. Here I am having ZOC, ZOD. I'm substituting those two values here and here. By substituting these values, we will get first this one, that is Rx plus j omega Rx into ZOC. ZOC is nothing but this one. ZOC means R3 by j omega C whole divided by R3 plus R5 plus 1 by j omega C. It is ZOC equal to, and the rest of point is here, R2. Here it is R2. So R2 into R4 plus ZOD. ZOD means this much, this much. This is ZOD. So R3 into R5 by R3 plus R5 plus 1 by j omega C. It is the expression. Now we have to simplify this. So from this, by simplifying, just look at here. Now I'm making here LCM at this RHS side, LCM. The same term I'm keeping and I'm making here LCM. So look at here, the same term Rx plus j omega Lx into R3 by j omega C by R3 plus R5 plus 1 by j omega C. This is the one term equal to R2 into LCM. I'm making here LCM. So this one into this one. R4 into this one. R3 plus R5 plus 1 by j omega C plus R3 R5 by this term. R3 plus R5 plus 1 by j omega C. Now this one will get cancelled. So I am having here this term and this term. Now look at here, I am multiplying this one with this one with this. So Rx into this one. So Rx into R3 by j omega C, this one into this one, plus j omega Lx into R3 by j omega C equal to I'm multiplying this R2 internally. So this one into this one, R2 R4. First I am multiplying only with this compound term into R3 plus R5 plus 1 by j omega C plus this one into this one, R2 R3 R5, R2 R3 R5. Now look at here, j omega will get cancelled. Now I'm multiplying this compound term internally. So the rest of the term here, Rx R3 by j omega C plus this one Lx R3 by C equal to this one into this one, R2 R4 R3 plus this one into this one, R2 R4 R5 plus this one into this one, R2 R4 by j omega C plus this term as it is, R2 R3 R5. Now look at here, I am taking this j within the denominator or having j. I'm like taking this to numerator, then it will become minus j. So Rx into minus j R3 by omega C plus Lx into R3 by C equal to R2 R4 R3 plus R2 R4 R5, the same point I'm getting, minus J R2 R4 by omega C plus R2 R3 R5. Now I'm equating real parts. Equate real parts. Just by equating real parts here at LHS side, it is the real part, 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 both the sides. So this one equal to Lx into R3 by C equal to R2 R4 R3 plus R2 R4 R5 plus R2 R3 R5. And here R2 is the common term from all. Just take it out. That is R2 into R4 R3 plus R4 R5 plus R3 R5. That is Lx into R3 by C. Finally, I'm getting here Lx equal to, I'm letting this term to this side, then C into R2 by R3 into R4 R3 plus R4 R5 plus R3 R5. It is the unknown value of inductance. Unknown value of inductance. Similarly, compare imaginary parts. Compare imaginary parts. Look at here, imaginary term. This is the one imaginary term at this side, and at this side is the imaginary term. So equate these two. So getting Rx into minus J R3 by omega C equal to minus J R2 R4 by omega C. Yes, with this minus J, omega C, cancel. Then finally we're getting Rx. That implies Rx equal to R2 R4 by R3. It is the unknown value. Like this, we can find the unknown value of inductance by using Anderson bridge.